Thank you all for being here. It's really a pleasure. We joined with my lab, University of Toronto this summer. And of course, things are complicated due to the pandemic. And still, I'm really glad that things are revamping. And it's a privilege to me to be a part of also the physics department in this community. And we all very much look forward towards developing potential collaboration and exchanges of ideas and discussions. So I'm really hyped about this. And so I'd like to seize this opportunity to tell you a little bit about our research efforts. And they in one way or another connect to this topic of quantum machine learning. And to provide you a little bit of a motivation for that. So I was promised this would work. Okay. This is sort of the backdrop. We would, one of the reasons I also came was within the Acceleration Consortium that was founded at UFT recently, and there the idea is that we would like to accelerate the discovery and design of matter, and the general underpinning components are, of course, the laws of physics that rule the whole thing. And we'd like to make use of computer simulation, of robots, of big data, and modern statistical learning, right? But at the end of the day, our applications are towards material science or chemical sciences or biomolecular sciences. So that kind of goal at the end of the day. So what you see here then is our progress. And of course, we are not alone in the field. There are many people trying to do similar things. But our view is really that we'd like to understand better the structure and the relationships in chemical compound space. And so that is related to quantum mechanics in the sense that when you solve, for example, Schrödinger's equations for the electronic structure problem or for nuclear systems, then these solutions, they are not fully independent as you go from one material to another. So it's basically different solutions to already the same Hilbert space, right? There's a larger space in which all of chemical compound space lives, if you wish. And so these solutions, they correspond to certain points, for example, in the observable of the energy, so the expectation value of your Hamiltonian, right? That typically is a minimum in the underlying variable space of nuclear positions and chemical elements, chemical types. And so here you have an illustration. There's a virtual reality animation of the 1,000 smallest organic molecules you could build, which would compose, if you wish, building blocks for larger molecules, right? So as you know, in chemistry, functional groups can repeat, and you might find the same local patterns again and again in larger structures. So these repeating patterns are something we'd like to exploit, and that's something that machine learning can do, right? And so this is what we are aiming to do, right? And so this is not to be confused with the application of quantum algorithms towards machine learning, right? So we want to use classical machine learning or classical algorithms for, I have to, I'm afraid, move closer to, okay, like this. We want to use classical algorithms to also solve for quantum observables, quantum properties, and possibly those quantum materials could then also be used again to build more economical hardware for quantum computers, right? And so there might be some loop, but in some sense, we are orthogonal to the quantum computing algorithms. Now, our alphabet is, in some sense, the periodic table. As you all know it, recently it celebrated 150 years, and it got an article in the New Yorker. Now, if you subscribe to the New Yorker, it's very rare that the natural sciences feature in this publication, this kind of journal. So I think it's remarkable that every now and then you find something. Now, you're probably familiar with this, right? We learned this in high school. I believe way too late, right? The alphabet, usually you learn in elementary school or even earlier. Why don't we learn the alphabet of the elements? I don't know why it has to come so late in the curriculum, but these are less familiar representations of the same periodic table or the same elements, right? Just arranged differently. Now, these here, this one or this one or this one, these are not wrong. They are not inconsistent with what we have, what we know about the elements. It's just a different way of structuring things. These are more such representations. And you see nicely here, maybe even more intuitive than in the conventional table, the sort of, this looks like a little bit like a damped harmonic oscillator or something, right? So there's this underlying structure, and this is something we can actually exploit, right? And often this reflects an underlying lower dimensionality. And this is actually known in material sciences. Pettifor, in the 80s, David Pettifor developed this Mendeleev numbering scheme. And so if you follow the lines he devised for the elements, certain properties such as the formation energy, this is formation enthalpy, the heat of formation of different materials, if you follow those lines in that order, you see that carbides or nitrides, this formation energy falls onto a linear relationship. And that property, actually, formation energy, is a very complex property. It's very difficult. If you wanted to calculate this from scratch, this is a real challenge, right? Yet, if you know just a couple of points here, you can easily interpolate because there's an underlying lower dimensionality. So this is very powerful, I think, because if you are in the business of designing new materials, let's say you wanted to find a nitride with a certain formation energy, then just by knowing this relationship, you can immediately read off that you should be using tungsten, a tungsten carbide to get that formation energy, right? And so the inversion problem can be close to trivial if your underlying dimensionality is low. And so this might have true implications for materials applications. This is not outdated research. Hardy Gross and Mikkel Marges just in 2016 published, revisited this one-dimensional periodic table for other properties, right? So the search for these lower dimensions in compound spaces is ongoing. Now, there's a famous quote from Dirac, which is well established, and it has puzzled chemists for a long time, that in principle, everything is solved, or most of it. And to a certain extent, I think this statement still holds, right? A lot of chemistry can indeed be solved with the laws that were developed at the time. So by Schrödinger and Heisenberg and so on. Now, there are various applications, various approximations we can make towards solving the electronic Schrödinger equation. And you have force field methods, semi-empirical methods, mean field methods such as Hartree-Fock. MP2 is a perturbation-based method, and explicitly correlated methods like quantum Monte Carlo or coupled cluster. And depending on the code you use, the basis functions you use, the system you're studying, the number of electrons you have in the system, you might have to invest different amounts of CPU time. Now, CPU time for the younger among you is directly proportional to money. Okay, this is an easy conversion. So the more wealthy you are, the more accurate your predictions are. Right? And the more accurate your predictions, in some sense, you could argue, the better your understanding of matter. Okay, so the better you can predict something, right? The more you understood it, in some sense. So in other words, the more prosperous you are, the deeper your understanding. So that's maybe a bit provocative, but anyhow, so this is sort of a landscape, right? And if you devise an interesting approximation to solving Schrödinger's equation, and this approximation is above this diagonal line, then even though it might be valid, it's less advantageous than using something that's already existing, right? So in some sense, this is also a Pareto front, right? You're negotiating, you're trading off the accuracy versus the cost you need to invest. And the most interesting solutions to your Pareto front or those solutions that lie on your Pareto front are the most interesting, right? Anything that's above could be done in better ways, in more efficient ways. Now, that means then also anything you have below here should be of real interest, right? If that could be a goal for research. Now, so density functional theory, another mean field theory, is indeed below Hartree-Fock, right, in terms of accuracy. And there's also a tight binding semi-empirical variant that gets very decent accuracy. And so Walter Kohn and John Popel in 1998 were awarded a Nobel Prize in chemistry for these contributions. And I should also point out that this 1 kcal per mole, this is a critical number. In terms of chemistry, it is difficult to go beyond 1 kcal per mole in terms of experimental uncertainty and combustion chemistry. So if you buy a big calorimetric device and you put it in your basement, you measure there, it's difficult to exceed, to become more accurate than 1 kcal per mole. So this would really be desirable to reach that. A typical covalent bond has something like 100 kcal per mole stored in terms of energy in it, right? So it's 1% roughly of the properties you'd be interested in when talking about materials behavior or chemistry. So what we are trying to do is to address this problem basically from two sides of the same coin. We think of this problem. Suppose you have a solution on some potential energy surface of a material like shown here in black. You could use perturbation theory to expand, to develop around a series around that point. And that's what we call alchemical perturbation, right? In particular, when you also change the chemical composition. Now, the nuclear charges as we have them in the periodic table are, of course, integers. But in our solutions to the electronic problem, your external potential, which accounts for the nuclear charges, you could actually change it continuously. So the quantum problem of the electrons does not care if your nuclei carry integer or non-integer nuclear charges. And so we can construct derivatives and higher order terms. And that is actually work that has a long tradition in chemistry, starting by Feynman and Hellman and Fukui, who also got a Nobel Prize in chemistry. Now, the other side of the coin is that you say, okay, suppose you have solutions on the empty symbols. Now, what is the most likely value of the black ones, right? And so that is a typical sort of Bayesian questioning. Given the solutions of all the others, what's the most probable value of the missing one? And that's what we can use machine learning for. So in supervised learning, Vladimir Vapnik and many others showed that given enough input, so nuclear charges and coordinates, and output, so for instance, observables such as the energy, if you have enough of those, you can infer for a new set of input coordinates, you can infer the corresponding label. And the bigger your training set, the better your prediction. So in some sense, we have these two coins, and you could try to create some drama here. I won't bother you with this, but just to briefly tell you about the smoothness of the chemical space, the smoothness of the quantum solutions in chemical compound space. Here's a numerical illustration of the N2 molecule. This is the most abundant molecule in our atmosphere, right? What you breathe right now is mostly N2. And its potential energy, the electronic potential energy, looks like this. As a function of the distance between the two atoms, you would observe this kind of shape. Now, this is just the electronic energy. I've subtracted the nuclear repulsion because we typically account for that just in terms of classical nuclear charges, Coulomb repelling each other. So that's trivial, and we focus just on the hard part, right? So this is how it looks like. It actually, as the two atoms come together, the electronic energy just levels off towards the atom, the energy of the united atom, right? So there are 7 protons in nitrogen, and the two together, they form the silicon atom, right? So as you fuse those two atoms together, you get the energy of the silicon atom. Now, I can also vary the nuclear charges, right? They both have 7 protons, so I can go to 6 protons and 8, and that's the CO molecule. Or to 5 and 9, that's the BF molecule. Right? And that then leads to this shape where the nitrogen is actually rich. And of course, it's perfectly symmetric by rotational symmetry. And I can construct now derivatives in my electronic density. It's the one particle electronic charge density distribution. And I have first, second, third, and fourth order derivatives here. And using these, I can then expand the electron density to predict the electron density of CO or BF. And that compares very well to what you would find if you actually calculated those. Right? So a Taylor expansion kind of approach works pretty well in chemical space. Now, we can use this to actually predict energy changes in real molecules, like shown here. And here you see the Taylor expansion, and I've made use of the Hellmann-Feynman theory. So the first order derivative just contains the external potential difference, and then the electron density, and then higher order derivatives only operate on the electron density. And so that's how it looks like. And so I can go from benzene shown here towards this molecule as well. So here you see a BNNB doped derivative. And the corresponding first order derivative would look like this. And we actually find that if I go towards this molecule or towards that one, you see that the external potential difference is simply has simply opposite sign. And that results in the first order derivative to have opposite sign. If I then take the energy difference between these two guys, so the energy difference between these two molecules, these terms cancel. Right? And so there's this symmetry in chemical space, right? If you look at these molecules, if you give them to a chemist and you ask them, do they have the same energy? The default answer should be no. They don't. They have different bonds. Right? But we find that using these arguments, there's this anti-symmetry relationship. And you can see that actually the second order term here contributes only very little. So this is the second order term in the electron density. It's the third order term in the energy. And so to a very good degree, these two systems are degenerate, but it's a broken symmetry. It's not a perfect degeneracy. Right? So higher order terms will then differ between these two systems. But just approximately, we then can construct constraints on the bonds because of this relation in chemical space. and these constraints were unknown, and so we have learned something about the structure of chemical compound space. So here's another example. It's not just limited to these flat benzene derivatives in the diamond crystal structure. You could construct similar mutations, and these two patterns here would also carry the same energy. Okay, with this, I'd like to tell you now more about the machine learning part. And this started in 2011. I organized a program at the Institute of Pure and Applied Mathematics at UCLA on the problem of navigating chemical compound space. And one of the participants was Klaus Robert Müller from Technical University Berlin. He holds the chair for machine learning. And so I confronted him with this question: how can we avoid this situation where every time we make a modification in a material, we have to solve Schrödinger's equation from scratch again and again without ever learning anything, right? It's sort of a frustrating procedure. And so he proposed that we use a simple machine learning model called kernel-rich regression. And the expression is like this: you estimate the property of a material M by summing over your training set. So every I is a training instance, a training material MI. And then this kernel function quantifies the similarity between your query material and the training material. And this kernel function is between 0 and 1. So if it's 1, it's identical. If it's 0, it's very different. And you get a weight then for every training instance. And this weight carries the units of your property. And there's a simple expression for this weight. It's the inversion of the kernel matrix of all your training instances multiplied with the reference property that each training instance carries, right? So it's as simple as that. Actually, I don't think it could be simpler. And once you've inverted this, you can then predict for any new material the property. And as you increase, so the sum runs from I equals 1 up to n, and n is the training set size. As you increase that training set size, your prediction should become better. Right? So if the prediction would not become better, then your machine would not learn anything. So that's sort of the definition of machine learning. So then the question was, what do we use as a measure of this material, and what do you use as a measure of similarity functions? And so for the material, I proposed a matrix now known as the Coulomb matrix, where you basically have an atom by atom matrix. Here it's illustrated for ethanol, and basically we put on the off-diagonal elements the repulsion between the nuclear charges of two atoms in the system. And this matrix measures or represents, if you wish, the material. So it's like every compound can be represented by such a matrix. And then this kernel matrix then measures the distances between all materials matrices, right? So in other words, we have spanned a matrix of matrices to represent this compound space. And that's where we interpolate. So if you interpolate then inside this chemical space, as you imagine, as the density increases around it, your interpolation should become more accurate. And so there is mathematical proof that the prediction error must decay inversely, and the leading order term is just this training set, the inverse training set to this exponent b. So in other words, if you logarithmize this, you should get a linear relationship of the log of the error with the log of the training set size, right? So it should look something like this. To come back to our Pareto plot, and one of the big advantages then is that once you use the training set size, a certain training set size to train your model, you can then use the model for new systems at practically no cost. So multiple orders of magnitudes faster than the traditional solvers in quantum mechanics. So this sort of the background, and now I'd like to tell you about 3 recent papers we've been contributing in the field. The first one is with predicting the structure, the geometry of molecules. Then we have a paper on reactivity, or 2 papers on chemical reactivity, and a paper on free energies. We basically think about chemical space. You can think about it in terms of an energy scale. It's measured here by temperature. So for very high temperature, you would have only elementary particles, and you would have fusion to change your stoichiometries from one system to another, or reservoir of elements. And then you have constitutional isomers, which have different bonding. So for a given stoichiometry, right, you have all these different bonds. And then we also have conformational isomers. For a given bonding pattern, you could have all the different dihedral angles you could imagine, right? And as your temperature becomes smaller, your system gets trapped in these local minima, right? With barriers sufficiently high that at that temperature, they will not be overcome. And so you can isolate these different species. Predicting these structures, we are basically trying to predict the 3D coordinates for different such constitutional isomers. And when you do this traditionally, you would start with some initial set of coordinates and then relax them in order to minimize their energy. Right? So you use the energy as the criterion to identify your structure. Now, we have been looking at constitutional isomers with this sum formula. And there's a data set we published in 2014 where we have coordinates for 7,000 of such molecules. And so this is how they distribute the density in terms of their energy. And this is how their geometry distributes in the moments of inertia. So the sphere-like molecules would be here, the linear ones here, and the planar ones here. And the way we solved this problem was by saying, okay, it's very challenging to predict the Cartesian coordinates of a point in space, right, as a function of the others. So there's a lot of arbitrariness, but it's easier than to work in internal coordinates. And we did this by constructing an atom distance matrix, and we predict the off-diagonal elements, so the distances between each atom pair, using the molecular graph as an input. So here we have a series of off-diagonal elements, and for each element, we train a machine learning model that uses the graphs as input to predict the corresponding distance. We treat these distances as if they were independent labels. But the training set was curated first such that these interatomic distances were minimized. So they were sorted by their size. So in this sense, the training set was consistent, and we could show that following a certain procedure, so we tried different graphs as input and different labels. So these are distances with and without hydrogen atoms. And then once you want to make a prediction, you get the off-diagonal distance, and then you have to reconstruct the coordinates from the distance matrix. There's a very good algorithm called DG-SOL that does that for you. And then we can construct the 3D Cartesian coordinates. And what we see here, this is maybe the most important, this is the learning curve. So your error systematically decays as you increase the training set size. The training set sizes are shown here. And we've also repeated this exercise for a different set of isomers with a different sum formula, and also for open shell molecules. So these have a spin that is it's not a closed shell molecule. So these could be magnetic, and you see that we can also learn the structure of such systems. Now, if you wanted to do this traditionally with the quantum chemistry method, such a geometry, predicting it is much more challenging than for such vanilla kind of organic molecules. Here you see a distribution of these intermolecular distances and the matrices. And you see there are some distances that are peaked here, very short distances. These are the typical covalent bonds between nearest neighbors. And then you see second nearest neighbors and all the distances to other atoms in the molecule, they tail out like that. Now, predicting large distances is much more difficult than predicting short distances. And this is something you see in this histogram of the error we are making in the prediction for the various interatomic distances. And you see the error is smallest for the short distances up here, and it's largest for the large distances. It's easy to explain that. The short distances are tightly bound by covalent bonding, and there's a very little variance, while the long distances, they can rotate a lot easily, right? It's very shallow energy profile, and so you will have a lot of variance for that. And so correspondingly, it should be much harder to learn. And that's also what you see reflected in these numerical results. So in some sense, the machine now tells you, gives you this feedback, look, there's some distances that are harder to learn than others. And the reason being, we know that that the energy is very shallow in these degrees of freedom. But if you had not known that so far, now you could infer that, right? Conclude that from the machine. So these are insights, right? The machine can tell you, and it should be consistent with the underlying physics that's happening here. We also applied this algorithm to predict transition states. So these are saddle points going from one product to another on a chemical reaction. And these are also notoriously difficult to predict. And such a simple algorithm can even tell you such structures. And we also applied this to crystals. So this is not restricted to molecules, right? Quantum mechanics also works for solids, of course. And you can see here the lattice constants, pairwise distances, unit cell length, they all improve the error decays with training set size. So we have here the mean absolute error for pairwise distance, unit cell length, and this is the root mean square deviation. So it's a more difficult part. With this, I'd like to go to chemical reactivity. And this is work which was done by my PhD student, Heini Heinen, who recently graduated and now joined Vector as a postdoctoral fellow, and he's present here in the audience. So all questions relating that part, I will immediately redirect to him if you're interested. So we've been working on this question. If you have a reactant, a chemical that would react in one way or another, we could imagine, for example, textbook reactions like an elimination reaction, so where X and Y leave and you have a double bond, or a substitution. So this X here gets replaced by a Y atom, right? So this Y atom is attacking here, and then the X detaches, and so there's a substitution reaction. Now these two reactions can compete. Okay, so these are competing reaction channels, and it's one of the key questions often encountered in materials and chemistry. Which one will win, right? What's going to be the main product of the reaction? How can you steer the reaction in one way or another? So we try to address this question. Which one is more frequent given a certain reactant? Can we predict this using machine learning? And there's also a chemical heuristic rule called Hammond's postulate, which relates the change in the structure of your compound as you go towards the barrier here. It relates it to the barrier height, right? So it postulates that there's a relationship in some sense between this x-axis and the y-axis, for which there's no obvious reason to postulate this. So in order to tackle this, we first created a data set that contained a lot of transition states for these two reactions using various levels of quantum chemistry. And we then trained machine learning models towards the elimination reaction. So in this direction, towards the substitution, predicting the barrier height, which determines the rate of the reaction. Okay. And so if the barrier is lower, right, then that reaction would occur faster. And so if you can predict that, accurately, then you could predict which one is going to be the product of the reaction. And you see here that with just thousands of examples, we reach a level of theory. It's not the 1 kcal per mole we were talking about, but the kind of quantum chemistry levels we've been using, they would only correspond to roughly 3 kcal per mole anyways. Now, you can see that we quench this error down to below 3 kcal per mole, but the activation energies we are talking about go up to 50 kcal per mole, right? So the error is less than 10% of the roughly of the magnitude of the property. So in the chemical space, we considered, we then used the model strain to include predictions for many more reactants. And we found that, so we had for training roughly the blue data set here, and then we predicted in total all the greens one. So with the quantum chemistry and the machine, we have the green distribution, or just with the prediction, the orange. And you see that in total, we expect that roughly 3/4 of all possible reactants would undergo an elimination reaction rather than the substitution reaction. So that is something we find for this particular group, the subset of chemical space, which we've considered, right? But we are not aware of any general rule or law of physics that immediately would tell you that, right? So this kind of frequency, the relative preference of varying reaction channels or competing reaction channels as you go through compound space is something we believe is not yet well understood. So this Hammond postulate I told you is about relating changes in geometry, such as changes in distances between atoms, to the activation energy. And using our model, we could then predict these, and we find that for SN2, this relationship, heuristic and empirical, it holds, but for the elimination reaction, it does not really hold. It's one of these chemistry rules. Sometimes they work, sometimes they don't, but you never know when and why. And so here we could, in this case, root this out. So finally, the last paper I want to tell you about is about these transition states. And this is something which is currently under revision in the Journal of Chemical Physics. Here the idea is that we don't only want to predict the barrier height, but actually also the structure and converge towards this really the barrier, the distorted geometry. And so suppose that you have for one compound or another, you have the entire profile. Can we now predict the entire profile of a new compound, right? And so again, like in the predicting the structure, we now have an error measure in angstrom, right, in geometry, and we are trying to converge to predict the energy and forces on the atoms, and we use these forces to optimize towards the saddle point height or towards the minimum. And here you see the learning curves for the transition states in green, as well as for the reactants. So the starting points, you see that we also get the geometry optimization right. And we can do this as a function also of how many of our convergence runs would actually complete, right? So if you start here and you try to find the saddle point, not all of these optimization runs will converge, right? And what you see is that the bigger the model we trained, the higher the success rate of the optimization run you obtain afterwards, right? So that would also indicate that increasing your training set improves the quality of the forces, even for transition states, which improves then the likelihood of successful optimization. To illustrate this further, so the complexity of things we've shown here for this species, the transition state geometry. So this at the top predicted. So this is out of sample just by the machine. There's no quantum chemistry in here. And you see here the normal mode for which we have the barrier, right? While here are shown all the other normal modes for which you have the minimum to have a true first order saddle point. And superimposed with this is a quantum chemistry calculation for reference to check how well you're doing. And you see a very fair agreement, right? So this is in this sense a success. So finally, I still wanted to tell you about the free energy predictions we made. If you take molecular graphs such as these, and you just generate one set of coordinates from such a graph, you will find all sorts of coordinates that are compatible with the graph. For each of these coordinates, you will get different solvation energy estimates using continuum models. So if you wish, this single graph will be consistent with coordinates yielding a variance here of more than 2 kcal per mole in free energy of solvation, according to traditional models. So we thought this is a problem, and we wanted to revisit our machine learning models to better account for the degrees of freedom we have in nuclear movement, right? So at finite temperature, of course, all your atoms will vibrate, and your conformers will change, and this will affect dramatically your energies, your energy changes due to solvation. And we wanted to include this in the model, and we do this in particular by taking reference to the statistical mechanical average you would have for any observable. And in particular, we take the average of structure. So averaging the structure during a molecular dynamics run, and in this way, we can now use this average structure as our input representation of any given compound. And so you would not take any fixed set of coordinates, but the average structure for isomer A or isomer B as inputs in order to infer for isomer Q the proper statistical label, which in this case would be the free energy of solvation. So we took an experimental data set of free energies of solvations. It's called the FreeSolve database, which was published by Mobley and others. And we used these experimental labels together with average structures obtained from molecular dynamics to train a model, so to get the alpha coefficients for averaged structures. And then for a new query, we would average the structure again, and then use the trained alphas to predict the label for the new out-of-sample prediction. And in this way, we also produce learning curves. There are different flavors here. I will not go into detail here, but you see learning on all these models, and they really reach an interesting level of accuracy. And you also see here in a scatter plot, so these are out-of-sample predicted versus true experimental energies we are predicting here. Now, we can compare this to other solvent models in the literature. In particular, Cosmo is one of the most popular one. They have errors of, at best, half a kcal per mole, but they are very expensive to calculate, right? And so with our model, we are an order of magnitude faster here, and as fast as this one. I should also mention that this model is not for free. It's not only computationally expensive, but also financially expensive to run this model. Also, I should mention this Cosmo RS will not improve as you add more data, while these learning curves would clearly indicate that if you were to add more experimental data, the model should further improve. Finally, you can use such a model to make predictions. So we took the model and we predicted free energies of solvation on the entire QM9 data set. The QM9 data set is that set I mentioned earlier, which we published in 2014. It contains 134,000 organic molecules. we predicted free energies of solvation for all of them, and this is how they distribute. And we can look, for instance, here in the simple alkanes, you see that these molecules are actually predicted to fly out of the water. So they have positive free energies of solvation, while here the most negative ones are these very polar molecules, just as you would expect. So if you did not know anything about polarity and aqueous solvents and so on, this is now what the machine would tell you if given just some experimental data you feed in. You can also investigate how the number of hydrogen bond donors, how the number of NH groups or oxygen atoms or hydrogen atoms affects on average the free energy of solvation you predict. And this corresponds also to what we would expect from chemical reasoning. I'd like to skip ahead of these two and come to the conclusion. I hope I could convince you that these learning curves are helpful measures of the quality of these models. In all, I think it's not too daring to claim that we have something in machine learning in the community. What's going on is basically that there's a fourth pillar in science, sort of which we are establishing. So the first one could be the experiment. The second could be our theories, right? The theoretical physics behind it, trying to explain these experiments. Then we have computer simulation, which could be considered a third pillar. And the fourth pillar would then be the statistical learning, trying to unite all of these other pillars and profit from all of them. These are some perspectives or reviews we've contributed. There's a lot going on. I think in view of the control of the accuracy and the speed ups we've been experiencing, I think if you were wondering if this is an evolution or a revolution, I'm rather in the revolution camp, but one can argue, of course, about this. So many people contributed to this. I've shown you work from Heini, who is sitting here, Guido von Rudolph and Jan Weinberg did a lot of the work as well as Dominic Lem and Nick Browning shown up here. I received a lot of funding from the various sources, and with this, I'd like to thank you all for your attention.